Please sign up to be notified of upcoming webinars, meetings, and other NETL RWFI activities by emailing us at netl.rwfi@netl.doe.gov and signing up for our monthly e-note that gives out all the information about upcoming webinars and meetings that are occurring at NETL, as well as funding opportunities around energy, workforce, and advanced manufacturing workforce and economic development topics. So with that, let's begin. First, a little bit about why we are here. This is the Energy 101 series for the NETL Regional Workforce Initiative, which Anthony, our next speaker, will talk about a little bit before Briggs White, our featured speaker, will talk about advanced materials and high performance materials. The Energy 101 series is really just an effort for to bring to you guys, our stakeholders, our colleagues, a better understanding of the broad array of different types of research that NETL is involved with, but in a simple to use format to break down kind of like the technical barriers of understanding some highly technical and highly complex research and make it into usable information for you and your stakeholders. We've done Energy 101s on rare earth metals, energy storage, sensor technology, modeling and simulation, today's will be about advanced materials, and we have plans to do a couple more in the next couple months on coal and CO2 products, and then an update to our advanced manufacturing research that we're currently doing at NETL. Again, there's an archive of all of our webinars on our website. So without further ado, we'll start with Anthony Armley that will tell you a little bit of background information about the RWFI and why we are here. Anthony and Briggs, just as a reminder, just tell me next slide and I'll go forward on the slide deck.
Okay.
Anthony?
Can you hear me?
Yes.
Can you hear me now?
Yep.
Okay. Thank you. So hello everyone, I'm Anthony Armley, Federal Coordinator for the Regional Workforce Initiative at NETL, based out of Pittsburgh. I'd like to thank you all for joining us today despite the tough circumstances. Before I give the floor to Briggs to talk about the material development and the research that we do here at the lab, I'd like to give you a brief introduction about NETL's Regional Workforce Initiative for those of you that aren't familiar. Slide. The mission of the Regional Workforce Initiative is basically it's an extension of our actual lab's mission of getting technologies to market. So we make it from a regional perspective. So we use the Regional Workforce Initiative platform to engage and collaborate with our key stakeholders in the Appalachian region who we feel are critical for the deployment of our technologies that are related to energy and advanced manufacturing. Slide map. Three main things that we try to do, with this regional workforce platform is collaborate, coordinate, and to communicate. So we collaborate with regional and national stakeholders and various partners around energy and advanced manufacturing. We focus on workforce readiness and economic opportunities in this region. We coordinate across the economic development and workforce development initiatives that are in place with NETL, as well as our federal agency partners and then the various national labs. And then the last piece is the communication to stakeholders' activities, research and funding opportunities related to energy and advanced manufacturing, as well as workforce readiness and then economic development opportunities. So we do this in a various ways. We put out a monthly e-note which talks about training opportunities, top news at NETL, upcoming webinars and events being held or hosted by NETL, and funding opportunity announcements that not necessarily just from NETL, but from across the Appalachian region that we feel our stakeholders might be interested in. So if you don't subscribe to the current e-note, just let one of us know, myself or Matt Garcia. You can send us an email. My contact information will be at the end of my slides, and we'll be glad to add you to that monthly e-note. We also do webinars on various topics. We host stakeholders that participate in our webinars. We do Energy 101 series, which is what you're on here with today. We talk about technical topics that you may not be familiar with that NETL does a lot of work with, such as the material development and research that we're going to talk about today. And we participate in stakeholder meetings, such as the Team Consortium. Our regional workforce initiative, I just want to make it known that it's in response to our current administration's priorities, which is to reskill Americans for the jobs of today and the future, and to improve STEM workforce, science, technology, engineering, and math. There's also a focus there on establishing apprenticeships in America. NETL has trained over, I want to say 1,200 people since 2007. We host the Mickey Leland Fellows, grad students, and even some different undergrad opportunities as far as internships. If you have questions or you're interested, please send me an email and I can get you contacted in connection with the right folks who run those programs. And then lastly, the administration's priorities on strengthening the cybersecurity of federal networks and critical infrastructure. So we work with the workforce review across agencies and workforce readiness related to cyber threats and cyber technology. This slide was updated recently because we've had some growth related to our metrics with the Regional Workforce Initiative. So we're up to over 400 individual, regional, and national stakeholders who've been participating and engaging with NETL. 154 institutions and organizations represented now, and then 200 plus have subscribed to the NETL monthly e-note that I was just talking about. We're really proud of that. That's grown substantially since we started this Regional Workforce Initiative back in 2017. And then there's actually almost 600 registrants to this RWFI webinar series, which we're very proud of. And lately we've been doing these about once every 4 to 6 weeks. And we've found the growth to be pretty substantial since we've had consistent webinars. Slide, please. I want to talk briefly about why we feel this Regional Workforce Initiative is so important, and it focuses on Appalachia. So historically, Appalachia has been a critical region for the United States energy, and we feel going forward it's only going to continue to do that. Strategically, it's very important for related technologies in supercomputing, advanced manufacturing, and energy technologies. And then we expect in the future to enjoy a manufacturing renaissance that you're already starting to see different things popping up, such as the plants that are going in Beaver County. An area that has, Appalachia is also an area that has been adversely affected by changes in energy extraction and related manufacturing activities. So again, right here in our backyard, we've got these valuable resources that can be used for much more than just energy. And you're starting to see a lot more with various manufacturing elements being incorporated. Slide. Some key outcomes to date since we started this initiative back in 2017 that we're pretty proud of. I'll just highlight a couple that I feel are most important. Consistent engagement with key regional partners. I talked about the metrics. The involvement NETL's had with our stakeholders has been very, very important to us, and the growth and the communication has been very productive, which has led to a lot more engagement, a lot more opportunities that were known about, and then new collaborative opportunities. Integration of a workforce work plan. We're taking our funding opportunity announcements that we put out here at the lab, and we're looking at it from workforce perspective. What types of opportunities could the technologies that we're creating and developing at NETL lead to workforce development and economic development opportunities right here in Appalachia? We don't want the jobs that could come about from these technologies to leave our area. We're trying to get ahead of that. And so I work with the technology managers here to identify technologies that are 3 to 5 years from commercialization and put together a workforce work plan that I can share with our local stakeholders, local community colleges and technical schools. That way, if they need to tweak their curriculum in order to have these jobs, have the skills ready for these jobs when they are commercialized, that we take advantage of the opportunities that could be right in our backyard. And then lastly, increased growth for potential collaborative opportunities as a result of this Regional Workforce Initiative. I've talked about that a few times already, and it's very important. Slide. So the last slide here before I send it over to Briggs White to talk about materials is I just wanted to give, for those of you that aren't really familiar technology and the core competencies that NETL is working on here. I wanted to give you just a brief run through. So NETL is the nation's only national lab, 17 out of 17 national labs devoted to fossil energy research. So coal, oil, and gas, those are our bread and butter. That's what we focus on. Our core competencies, our main goal with our core competencies, get these technologies that we're working on advancing, get them to market. And so you look at the coal, some of the things we're working on with coal: carbon capture, carbon storage, advanced materials. You'll hear about the advanced materials, of course, today. Advanced computing, water management, extraction of rare earth elements from coal and acid mine drainage. And then as far as oil and gas, we're doing research on methane hydrates. We're doing research offshore, onshore, unconventional types, and enhanced resource production. There's a lot of different things that NETL does that we're very proud of. We have a very strong systems engineering and analysis group. We do modeling and simulation for other organizations. So if you have any further questions related to what types of work NETL is doing, send me an email. I'd be glad to talk about it a little bit further. And slide, please. Here's my contact information. Again, feel free to email me, call me. Let me know if you have any questions related to anything I talked about today. So I'd like to move on with our featured presentation today related to advanced materials and Briggs White. Thanks, Matt.
Thanks, Anthony. So Briggs, you're up next. I will let you introduce yourself, and without further ado, Briggs White.
Very good, Matt and Anthony, for that introduction. Hello, everyone. My name is Briggs White, and I'm pleased to provide you this overview of our DOE-sponsored high-performance materials program. I've also advanced manufacturing in here because advanced manufacturing really is the enabler for putting these materials into the ultimate commercial applications. But this program is making real investments in the material supply chain, particularly the high-temperature material supply chain, that enables good jobs and economic activity, both for the region and for the nation. Jump to the next slide, please. So I just wanted to build on what Anthony shared with you. We have a number of research campuses at NETL, and I just thought maybe it would be useful for you to understand our footprint specifically with respect to materials. We have our 3 R&D organizations, one in Albany, Oregon, one in Pittsburgh, Pennsylvania, and one in Morgantown, West Virginia. In Oregon, we have substantial materials characterization and manufacturing facilities. These are relatively large-scale laboratory facilities that provide a really nice technology transfer opportunity where if someone has a good idea or technology at the lab scale, can be tested out and validated at a larger scale, which provides a little closer line of sight to ultimate commercial application. Some really impressive manufacturing capability there. In Morgantown, we have supercomputing resources. Just refreshed our supercomputer there. And we also have high temperature facilities where we can simulate different power plant systems. So you can actually test a material in something that's simulating a real world power plant environment. Also tends to be a lot of overlap in terms of similarity between aviation related systems, for example, jet engines. In Pittsburgh, we have a functional materials capability. In particular, we use that for high temperature sensor materials. And we also have a dedicated resource related to machine learning. So more and more as data analytics becomes a trend that we want to leverage for a variety of reasons and applications, we have a dedicated resource base in Pittsburgh that we can use specifically for materials in addition to other things such as subsurface related activity. And then finally, in both Morgantown and Pittsburgh, we do both program and project management on behalf of DOE. You may know that NETL is a government-owned, government-operated national lab, unlike the rest of the national labs. And I'm actually a federal employee, which allows us uniquely to work hand in hand with our headquarters counterparts in DC to manage programs. So in this case, I manage the materials program on behalf of DOE's Office of Fossil Energy. I also coincidentally manage programs on energy storage, the brand new program in the Office of Fossil Energy, and our water management program. Next slide, Matt. Our materials program is our mandate from Congress is to enhance the nation's supply chain first and foremost, supply chain is written right into our congressional guidance, and so that's where we spend a lot of time. And what are we using these high temperature materials for? Mainly for power plants, particularly fossil-based power plants. Although we recognize that these materials have a wide range of applicability, particularly the high temperature materials. And so we do a lot of activities, whether it's computational materials design, which really goes to all of our different work. Some just pure computational materials, but also using more and more data analytics in combination with very detailed mathematical modeling. And we do that both for the functional materials and moreover for the structural materials. We do a lot of structural material work. And then we use advanced manufacturing where necessary. And advanced manufacturing is really a very broad term. It could go much beyond additive manufacturing. In this case, we have some samples that have been built up by Oak Ridge National Lab of some nickel superalloys using additive manufacturing, but also in other parts of our program, we do advanced welding, we do extrusion, we do casting, making the ingots themselves before they're turned into the different components and so on. So a lot of, quote, advanced manufacturing to enable the components to be made of these advanced materials. And what is all of this? What's the overall objective? In the middle of the slide, you see we're trying to make these power plants and more generally systems that are made with these materials to be able to be more flexible. We're trying to improve the efficiency, and that helps both in terms of using less fuel, but also reducing emissions and improving the cost of electricity that results from these systems. We're trying to drive down the upfront cost of putting in these advanced materials. They tend to cost more. And so if you're trying to get that advanced performance, you need to try to reduce the cost to try to improve the deployment. And then finally, asset management. These materials tend to extend the life of assets because they can enable more flexible operation. That helps a lot with asset management. Next slide, please. What is the fossil energy materials supply chain? So it's a significant set of entities in our national economy, around $8 billion of domestic value, employing over 30,000 employees. You know, clearly there are a lot of there's a lot of different sectors that come together in creating the initial alloys, which ultimately finished and then turned into components and ultimately create. Here in this graphic is we've used some information from the Bureau of Labor Statistics to try to give you a sense of the geographical distribution, sort of a heat map of where are those jobs. And what you see is, as Anthony said, there's quite a bit in Appalachia, also along the Gulf Coast in the south, a considerable amount of welding and other things primarily related to oil and gas, but lots of advanced alloys being used there. And then up along the Great Lakes in the upper Midwest, we have some additional hotspots of activity. But really, you know, given this is a DOE program, is a national program, and so you know, we think that our work has a broad reach into the supply chain around the country. But clearly, there is a regional concentration of related work here, and you know, a considerable benefit to the economy. Next slide, please. Clearly, the materials we're developing are useful in power plant settings, but they're also useful in other applications. And I think here, clearly, there's a strong regional footprint in some of these industrial sectors. The two biggest sectors, specifically for superalloys, there's a number of different materials that we focus on, but you know, the superalloys, primarily the nickel-based superalloys, are really projected to show some growth. We're looking at a $7 billion market in 2023. And the primary drivers are gas turbine-related machinery, so that would be either in domestic or military aerospace applications, primarily jet engines, and then industrial gas turbines, which so those are the land-based power generating turbines. And then after that, we have some other industries which are prevalent, particularly in the Appalachian region and up along up along the Great Lakes in automotive, industrial, which could be, for example, petrochemical manufacturing and other things, oil and gas, etc. So a lot of strong regional footprint associated with working on superalloys, which supports employment, and supports the economy. These materials really enable a lot of value-added products to be generated in the economy, and they almost all require manufacturing in one way or another in order to actually create the components out of these superalloys. Workforce is really critical, and perhaps we can kind of initiate a discussion as part of this webinar. I was really pleased to share our program overview with you because we would like to hear more about maybe where the workforce gaps are and how we can make sure that we're developing a workforce that can come along with these advanced materials and enable them to ultimately be generated in the economy. Next slide, please. This is a projection, the latest projection out of DOE's EIA, Energy Information Agency. And so this is the 2020 reference case. This is a projection out to 2050 of electricity generation based on the fuel. And what you can see is after some declines in coal and nuclear here, and particularly recently, things level out around kind of the mid-2020s and stay in the mix out into the future. Natural gas is projected to grow, but in particular, what stands out is that the renewables, the green part of the pie, grows quite a bit. And so the implications here are that fossil fuels will remain in the mix, at least domestically in 2050, and actually globally, it's even more growth than this. And the other takeaway here that I'd like to call your attention to is that with the additional renewables creating electricity, those traditionally base-loaded assets, coal, nuclear, and gas, will have to operate in a much more flexible regime. So a lot more cycling, and perhaps the addition of energy storage and other advanced capabilities that can help the grid work in a synchronous manner. Slide, please. So what is today's grid made of when we're talking about fossil power? Large-scale power generating units are natural gas combined cycles, of which there have been many build-outs in the last decade, and pulverized coal power plants. And within our materials program, we look for opportunities to make investments that will have broad applicability. And we've identified that there are many common components within these two sets of power plants. So our existing fleet actually has a lot of commonality, particularly in the steam cycle. So in the case of a pulverized coal plant, you have a boiler where you're taking heat and raising steam. On the back end of a natural gas combined cycle, you take the heat coming out of a gas turbine and you take that waste heat, if you will, and rather than just wasting it, you create additional steam and then run a steam turbine to create power, very similar to a coal plant. So a number of common components between those two systems. If we advance to the next slide, we're going to go over some of the challenges and solutions. So the various market segments that we focus on in the materials program are the existing fleet, just reviewed that, and also new generation, next generation plants. There's a lot of different potential next generation plants, both fueled by coal or gas, or perhaps even other fuels. For example, in the case of supercritical CO2, there's interest for concentrated solar power, for example. Nuclear is interested in a supercritical CO2 power cycle. And, these advanced cycles almost uniformly across the board require advanced materials. And in particular, the nickel superalloys wind up being enabling for the next generation plants, which tend to have much higher efficiency, and ultimately that reduces emissions and so on. The technical challenge areas, I've highlighted a few of the ones that resonate most strongly within our program. Clearly, there are other ones such as cybersecurity, which are very important, but are not a key focus of this particular fossil energy sponsored program. Our challenge areas include operation and performance optimization, asset utilization, condition-based management, and performance improvement. Next slide, please. these power plants made of. High temperature alloys are really the bread and butter of fossil energy power plants, and the materials that we focus on in the program. At the lower temperatures, we might be looking at a low chrome steel or a ferritic stainless steel. And then as you move up in the temperature regime, particularly above, I'd say 400 degrees Celsius, then you get into some of the advanced stainless steels. And then ultimately, when you're getting up and around the 700 degrees Celsius range, you're getting into some of the nickel-based superalloys. So the program really looks at the range of alloys, particularly the high temperature materials, given our congressional guidance to focus there. And those tend to be enabling for these advanced cycles. But we work on it in a number of different dimensions, whether it's trying to understand how we can bring down the cost of the alloys to improving the performance of some of the lower cost candidates so that we can ultimately bring down the cost of some of the advanced power cycles, make them more attractive for market deployment, but also understanding the materials, whether manufacture them, but also how long they will last in service conditions so that we can understand better when components are near the end of life and perhaps need to be taken down during a controlled outage for refurbishment or repair or replacement, as opposed to a forced outage where the plant comes down and there's a loss of electricity to the grid. It's a reduction in reliability overall. Next slide, please. You can advance one more into a couple of slides reviewing the program, and then we'll do a couple of highlights and then wrap it up. So the program, as I said, is focusing on market segments associated with the existing fleet and with the next generation. We have objectives for the existing fleet related to maintaining the cost competitiveness of existing assets. Some of the barriers, again, are aging infrastructure. Many of these plants tend to be 40 or 50 years old. They were built to be run in a baseload manner and are now being asked to operate more flexibly. Unpredictable outages, costly repair. We do some work on trying to improve repair techniques and reduce costs associated with those. And some advanced technologies are associated with the solution set there. Under the next generation plants, here we're trying to commercialize novel plant efficiencies greater than 44% efficiency. That could be through an advanced steam cycle, a supercritical CO2 power cycle, or perhaps coupling advanced power cycles with different heat sources, for example, chemical looping combustion, etc. The barriers are, making sure that the alloys have the technical capabilities to withstand both the temperature and the cycling, but also a barrier associated with the high cost, which reduces the market suitability for those alloys. And then the domestic supply chain is really critical. We've been working for over 2 decades in concert with industry to make sure that the U.S. has a domestic supply chain of high temperature materials that is ready to provide not only raw forms of materials, but also the finished components that can be fabricated into finished systems such as power plants, but also supply chain is, of course, serving many other sectors of the economy, including aviation, et cetera. For the solutions, high temperature, high performing alloys, we're coming up with new alloys, working on how, and then also a lot of work on process development. So, opportunities, we around 50 projects in the portfolio. And these projects are developing solutions that impact full operation and extend the life of assets. And they do that through a number of different ways. We talked a little bit on the previous slide about high temperature, high performing alloys. We're doing that through developing additional alloys, doing full scale manufacturing trials, and also the characterization of those materials, and developing new code cases. Typically, these materials have to be certified, if you will, by governing bodies before they can be put into the application. That creates a real barrier for the supply chain to get advanced materials out into the commercial marketplace. And so invest in developing code cases and collaborate heavily with our partners in that regard. Computational tools, alloys and process development, lots of materials modeling. It spans everywhere from the atomistic scale all the way up to finite element analysis of full-scale manufactured components. A lot of work on data analytics in particular lately. Continuing to go around our challenge circle here. Lots of work on advanced manufacturing, both enabling how do you advanced manufacture, in particular additively manufacture some materials where there's just not a lot of experience there, and maybe we need to develop even new additive manufacturing processes that have the throughput to be able to make components at the large scale required for power plant applications. A lot of work on repair processes. Of course, welding is nothing new, but advanced welding and the workforce associated with it is very important. So more and more we're thinking about how can we make sure that there's a well-trained workforce associated with welding these advanced materials where there's not a lot of experience associated with them. And we want to make sure that the welding, particularly for the existing fleet, but also as we're thinking about manufacturing new plants, that we have the technologies and the workforce available there. And then component materials life prediction, in particular, in concert with data analytics and real data coming out of plants, we're developing models both for the materials, the components, and the processes to make sure that given a certain set of plant history conditions, we know how those materials and components are going to stand up. So that at the end of the day, we can take action to make sure the grid and the plants are operating as reliably as possible. Next slide, please. So just revisiting some of the themes, we're really focused on improving cycling. That's a major transition for the fleet. And of course, any new asset that's built is also going to have to cycle. So we've done quite a bit of work here. We have an example from Alstom on a very thick-walled component. Thick materials don't tend to cycle very well. So in this project, we were looking at ways to try to make a thick-walled header, which is essentially a really thick-walled pipe made of metal, cycle better, and trying to mitigate damage that can occur there. Enabling high-efficiency cycles. This picture in the middle is courtesy of EPRI, and this was a project we did looking at oxidation and corrosion of metallic heat exchangers for supercritical CO2 power cycles. Those are really high-efficiency power cycles. They tend to have large heat exchangers in them, which drive up cost. So one way to reduce cost is to try to make them as compact as possible, which requires making really thin sheets of material or other advanced manufacturing processes to try to improve the overall efficiency of those heat exchangers and hence reduce the amount of metal and the total cost of those systems. And so there's been a lot of work on the material side to make sure that those really thin materials can withstand high temperatures and process conditions. And then reducing manufacturing costs. Here we have an example from the Energy Industries of Ohio. They lead a large consortium focused on the Advanced Ultra Supercritical Component Manufacturing Project. And here we're focusing on doing the final full-scale manufacturing trials so that we understand the yields, the quality, et cetera, associated with manufacturing full-scale components for power plants out of the materials required to make a advanced ultra supercritical steam power plant. That would be the highest efficiency power plant design available based on steam. So really kind of a crowning achievement in that flagship project in the portfolio. Next slide, please. All right, and so now we'll just go through a couple of portfolio highlights and then we'll wrap up. So we're developing the material supply chain for the future. So focusing on the nickel superalloys, a number of different projects there. And 2 years ago, we ran a funding opportunity announcement that started off with some phase 1 projects, each with $1 million of DOE money plus cost share. Those projects will have 18 months and will develop the feasibility of making lower cost nickel-based components that have improved cyclic durability. A number of university and industry partners in that effort. Really pleased with that. And so those projects will go through a competitive down select next year, and the phase 2 awards will be made with $5 or $10 million of DOE money. We also have a number of other projects in the portfolio related to nickel superalloys, whether it's characterizing materials, doing modeling, doing additive manufacturing of nickel-based components. And then we have, as shown on the right-hand side of the slide, our ComTest consortium, which really does show the geographical distribution of the project team, but also reflects consistently with the supply chain graphic we saw a little bit earlier. So showing the kind of the national reach, but also the regional concentration associated with these high temperature materials. Next slide, please. We have a growing portfolio of work associated with the existing fleet. Existing fleet is really important because we have a ready market there. A large number of coal and gas plants, but also a large number of other potential market segments that can use these technologies. Here we're working on technology solutions that we think can help the existing fleet. And those include the similar metal welds, whether made through additive manufacturing or more generally advanced manufacturing. Doing advanced manufacturing in and of itself of different kinds of joints, maybe with or without the dissimilar metals, but using advanced manufacturing to do it faster with less labor and improved quality. So that helps the cycling. Surface integrity, I've just got a couple of projects highlighted under one bullet here with Oak Ridge National Lab, NETL, and EPRI, focused on steam side exfoliation, whether through shot peening treatments or different additives to the water chemistry. Those can help with reducing scale formation and hotspot formation. And then under the data analytics, growing volume of work in the portfolio associated with that. And here we have a project that's focused on using data in collaboration with a company called SPS. They actually have real plant data. And we're using high performance computing through a program we call the HBC4 Materials Program, where we're using high performance computing assets at Oak Ridge and NETL in combination with data analytics and that real plant data furnished by SPS to predict component lifetimes. So pretty exciting work there. We have a funding opportunity announcement that we announced this year. It's currently under merit review that will also support existing fleet, primarily focused on the dissimilar metal welds and the surface integrity. Next slide, please. So in review of the portfolio, this portfolio has a broad reach. And in addition to the existing and new fossil-based power, I just wanted to lift up that we do have some projects and some technologies in the portfolio that reach well beyond fossil power. And so just as a couple of examples, we're doing additive manufacturing of an advanced nickel superalloy called Hastelloy X. So there we would be trying to understand the various parameters associated with manufacturing those materials with additive manufacturing, on the microstructures, the mechanical properties, ultimately enable those advanced materials to get into applications. IGT stands for industrial gas turbine. So in that case, that would be a power-based, a land-based power generating turbine, but also could be used for an aviation-based application. Down below, we have process modeling of Haynes 282. Haynes 282 is also a nickel superalloy. Here we're using process modeling as opposed to the actual manufacturing. This helps with, for example, large-scale casting. And so here we have a different kind of manufacturing process, but also with additive and some other manufacturing techniques. And that can be used, again, in power-based turbines, aerospace, et cetera. Rapid testing of austenitics and ferritics. So here we have some different classes of materials. These are referring to high temperature stainless steels, a little lower temperature capability, but also a lot lower cost. And that can help with a huge range of applications, not just as we've noted here in power-based turbines, and a host of other industrial applications. And then life prediction modeling, which also has a huge range of applicability, for example, the chemical processing, petrochemical applications. And we had a small business funding opportunity in this space this year. That's currently under merit review, and that was specifically focused on the supply chain, where we would require a minimum focus on fossil-based applications, but clearly that supply chain would be able to service a broad range of industrial applications. Next slide. So as we wrap up, I just wanted to leave you with a slide or two on engagement. So this program, routinely engages with stakeholders, and through this mechanism, I look forward to hearing any feedback or continuing or initiating any new engagements that can improve the objectives of the program. This really starts with a routine engagement with stakeholders, and so we participate in a lot of forums, whether technical forums or with stakeholders. We do quite a bit of strategic analysis to quantify the impacts. We showed some of the value chain mapping that we've done, and we're trying to better understand who is in the fossil high temperature materials value chain, but also how it overlaps with other application spaces so that we can advance objectives related to technology transfer and commercialization, and also so that we can connect with the most opportunities and the most potential partners to move some of those technologies forward. We're trying to hone the value propositions for our existing portfolio, but also identify new opportunities as we can move forward. So again, we would welcome your input. There's a lot of different ways to partner with us, whether that's directly with the lab. I mentioned several different funding competitions, and we will continue to offer additional funding opportunities moving forward. We haven't done an RFI or a workshop in a little while. We had a workshop 2 years ago on the high temperature materials supply chain. So it's probably time for us to reconvene and do one of those again. Look forward to engaging with us in a format that's suitable. And then we have an annual project review meeting. This year it has been postponed. We're looking to reschedule that. But that is a great mechanism to learn about the program, network with others to propose ideas in response to our funding opportunities, and then give us feedback. And we post all the presentations after the event, so you would be welcome to our website, and you can download the latest presentations from last year's meeting in anticipation of potentially attending for the next meeting that we hold. Next slide. I'd just like to leave you with some contact information. My contact information, you have Robert Schreckengoss. He's the program manager for this materials program at DOE headquarters. You also have Patricia Rawls. She's the team supervisor for the federal project managers that oversee all of the projects in the portfolio. And then you have our website link at the top. So in addition to the RWFI website links that Anthony and Matt showed you earlier, we have a website specifically for our high temperature materials program. It falls under the umbrella of our cross-cutting research programs. And you would be welcome to review any of those materials and let me know if you have any questions or comments. With that, I'll wrap up. Thank you.
Thanks, Briggs. And we're now going to can you hear me?
Yep.
All right. So we have a little section in all of our Energy 101 to try to have a dialogue with the guest speakers or the focus speakers on some of the workforce implications of their research or the research they presented. So we're going to try that here. We may not go through all these, but for example, what type of training did you have before you started this, and what type of training do tech managers have in general, and then specifically around the cross-cutting portfolio that you have?
So I have a PhD in high temperature materials and materials science. And so I came to NETL initially wanting to work on solid oxide fuel cells and managed projects in our project management organization for around 10 years. And then more recently, have been the technology manager for a number of the cross-cutting programs, including this materials program. And I think in terms of training, in addition to the education, certainly on-the-job training, but we also go through quite a bit of structured training related to, for example, understanding technology maturation, portfolio analysis, et cetera.
So immediately when people think about the cutting edge research that NETL does, they probably think of the scientists and PhDs like you working on the research and discoveries. But you touched upon this a little bit. What type of downstream workforce activities do you think the successful deployment of technologies like advanced materials, but others, could have? Like, what do you see personally as a technical workforce in some of your crosscuts, and what do you think specifically around advanced materials?
Well, I guess the first thing is I would really appreciate any input that the stakeholders involved in this webinar and the RWFI more generally have to share in that regard. But nevertheless, my perspective is that the workforce needs derive from the markets. We want people to have jobs, and conversely, an understanding of the gaps. And so while I understand the gaps a little bit less than I would like, in terms of the market needs, certainly on the super alloys, the advanced materials, we saw that there's a significant amount of growth in the gas turbine related application space. And so I think that clearly that could provide a nice workforce opportunity. And those advanced materials tend to be pretty challenging to work with, whether it's welding, additive manufacturing, casting, extruding. So I think that those kind of forming opportunities are clearly opportunities for workforce. I think in the more traditional materials, say the lower temperature capability materials like stainless steels, I think the application space is much broader. So there we might get into things like automotive applications, chemical processing, et cetera, where perhaps a lower cost material can find its way into the application. And those might be some of the material classes we would be looking at.
Yeah, and so you touched upon this on in your presentation, and actually this has been something that's been brought up in a number of different crosscut presentations, is that a lot of the research kind of revolves around, or as an outcome for a lot of the research that's done at NETL, is more efficient processes, more energy efficient processes, or more energy savings that come out of the research that NETL is doing. Can you maybe talk about what the knock-on effects of energy efficiency and cost savings are to an industry or a company in general? Like, obviously that's a good thing, but is that something that's also a focus of NETL research?
Sure. So I think we could look at it actually in two dimensions here. We can think about the materials supply chain, and clearly efficiency, or more generally, let's say the yield and productivity of that supply chain, is critical to it being competitive, as well as enabling those advanced materials to be widely deployed in the commercial marketplace so that we all receive the benefits from them in terms of improved environmental performance, reduced cost of electricity. In the case of aviation, it would be reduced fuel burn, which might result in a cost savings that could be passed on to the traveler. In terms of power plants in particular, nearly all of the applications of these advanced materials result in an improvement in efficiency. Even for the existing fleet, we might think about material upgrades, for example, that allow a power plant to operate at a higher temperature and more challenging environments and so on. So I think, the impact of energy efficiency in a power plant setting, at least in my mind, first and foremost, it's cost of electricity. If we can use less fuel and we create lower cost electricity, but right behind it is the cleanliness associated with creating that electricity. If we improve the efficiency, then that makes it that much easier also to potentially do carbon capture and other kinds of pollution mitigation technologies on the back end, because if you have less to clean up, then that means the mitigation technology becomes that much cheaper.
Okay, and final question, and this is kind of more of a broad question. What do you think the biggest challenges in commercialization of a lot of the technology around advanced materials? Where do you see this going in the next 10 or 20 years from now? Where would you like it to be?
Well, I think that with commercialization of these materials, for the advanced nickel superalloys, I think the pathway through natural gas-based systems and through the related broader application space, such as aviation, clearly is a potential pathway. And with the growth in those sectors, I think that we could see some commercialization of technologies in that space, and we should leverage that. I think clearly some of the technology trends, such as data analytics, can be a tailwind for advancing the research. And so we should leverage advances in supercomputing, for example, the investments that DOE is making to reach exascale and supercomputing, also data analytics. Clearly, we should leverage those technology trends. And then on the existing fleet, I think that clearly cost is king. And so reducing the cost of these materials it is important. And we need to make sure also that the domestic supply chain has what it needs in order to be competitive, whether that's a trained workforce or the advanced manufacturing capabilities, whether it's extruding, casting, additive manufacturing, in order to be competitive in a global marketplace.
Well, thank you, Briggs. Thank you for taking the time to discuss a very complex set of research that NETL does on advanced materials in a very easy way. So thank you very much. And with that, we'd like to thank you guys on the phone today for your participation as well, too. And then, again, just some reminders. Again, if you need updates, please sign up for our NETL RWFI e-note by emailing netl.rwfi@netl.doe.gov. Again, the webinar will be posted hopefully sometime next week on the RWFI website. And then finally, we have a webinar. Our next webinar is going to be in May, and that's going to be a presentation of regional and national data from the 2020 U.S. Energy and Employment Report from, and the presenter there will be David Foster. He was a former labor and workforce advisor for DOE, and he is currently a distinguished associate at the Energy Futures Initiative. And that'll be May 21st from 11 to 12 p.m. Eastern Standard Time, and look for that information being mailed out to you soon. Thanks again, everybody, and I hope you guys have a great day, and will join us next time. Thanks.